Around 65 to 68 million years ago, the late Cretaceous period marked the final era of non-avian dinosaurs. When an animal dies, the law of decay takes over. Soft tissues, muscles, blood vessels, and internal organs decompose rapidly, broken down by scavengers and microscopic bacteria. Biological material is completely stripped. Electron microscope view shows something that defies that standard model: a flexible, translucent network of blood vessels containing round, red microstructures. And these vessels came from a 68-million-year-old Tyrannosaurus rex. Under standard geochemical models, biological polymers and proteins cannot survive that long. Entropy and biochemical breakdown dictate that organic material degrades completely within a fraction of that time. This is paleontologist Mary Schweitzer. By treating fossilized bone fragments with weak acid to dissolve the mineral matrix, her team exposed surviving soft tissues that researchers had never thought to look for. Understanding how dinosaur bodies actually functioned requires us to look at the specific, extreme geochemical and cellular conditions that can hit pause on the clock of entropy. To reconstruct the internal systems of extinct giants, we must look past the skeleton itself and access the molecular archive within the stone. Before analyzing direct soft tissue, we have to establish the baseline of what hard bones alone can tell us about an animal's physiology. Take Deinonychus, a 31-foot late Cretaceous crocodilian that shared its habitat with the last dinosaurs. This diagram illustrates a cross-section of fossilized bone. Paleontologists use bone histology to analyze concentric bands called lines of arrested growth, or lags, which can be counted much like tree rings to determine the animal's age and metabolic rate. The histology of Deinonychus proves that it achieved its massive size through a prolonged 50-year growth period, maintaining a standard reptilian metabolism, rather than the accelerated growth rate seen in its dinosaur contemporaries. This phylogenetic tree demonstrates another technique called bracketing. By examining the closest living relatives of dinosaurs, crocodilians, and birds, researchers can infer the presence of shared, unpreserved soft tissues like gizzards or complex lung structures. Skeletal indicators offer specific evidence. Scars left on the surface of bones allow researchers to map out muscle attachment points, making it possible to reconstruct the powerful tail musculature of large theropods. Bony rings found in the eye sockets, known as sclerotic rings, provide a hard tissue metric for the size and external appearance of dinosaur eyes. While skeletal analysis and phylogenetic bracketing provide a robust structural framework, they remain indirect inferences. They tell us what the soft tissues likely did, but they are no substitute for direct preservation. Finding direct evidence requires zooming into the molecular level, where highly specific cellular microenvironments manage to protect biological polymers from decay. This is a Tyrannosaurus rex specimen, known as B. rex, excavated from the Hell Creek Formation. It is the fossil that yielded Schweitzer's isolated soft tissue. This animation shows the process of demineralization. By soaking the bone in a weak acid, the mineralized matrix dissolves, leaving behind resilient biological structures. As the rock melts away, original organic structures emerge, revealing collagen, elastin, and heme shielded for 68 million years. This survival is due to molecular shielding. The extreme density of the outer cortical bone creates a physical barrier, preventing decay-causing microbes from reaching the proteins trapped deep inside the matrix. The demineralization of the B. rex femur revealed a very specific type of tissue lining the marrow cavity, medullary bone. This is a modern female ostrich. When female birds prepare to lay eggs, they grow a temporary calcium-rich layer of medullary bone inside their legs, providing a ready supply of minerals for eggshell production. Finding this exact tissue inside the B. rex specimen proves the animal was a pregnant female, confirming a direct link to the avian reproductive cycle. Furthermore, because medullary bone has been found in subadult dinosaur specimens, we know that these animals reached sexual maturity before they finished growing to their full adult size. Molecular shielding isolates ancient proteins, allowing direct physiological comparison between dinosaurs and modern avians that we could never achieve by looking at bones alone. While molecular shielding protects microscopic proteins inside bones, the macroscale preservation of entire organ systems requires a completely different geochemical mechanism. This is Scipionyx samneticus, a juvenile theropod. Within its abdominal cavity, you can see the mineralized intestines and the reddish stain of its liver. The detail allows researchers to identify an avian-like layout, with intestines positioned much further forward than previously hypothesized for reptiles. This level of preservation is driven by a process called phosphatization. Shortly after death, gut bacteria drive a reaction that rapidly replaces the original organic tissue with calcium phosphate minerals. This reaction requires a very specific environment. As seen in this simulation, the curtis sinks into acidic, oxygen-depleted water. This chemistry essentially pickles the tissues, freezing their three-dimensional volume before they decay. This exact phosphatization mechanism applies to another extraordinary discovery, a fossilized dinosaur brain endocast found in England. The specimen belongs to an iguanodon, a robust herbivore similar to this skeleton, found in a geological formation dating back 133 million years. This 3D cutaway illustrates the preserved endocast. Because the dinosaur's head was submerged in stagnant water, calcium phosphate crystals replaced the meninges, the brain's protective serous membranes, and even partially preserved the actual gray matter. The brain tissue appears pressed tightly against the brain case, which might imply a larger brain volume and higher intelligence than typically assumed for dinosaurs. However, researchers recognize this could be an artifact of the tissue settling as it decayed. Phosphatization overrides normal decomposition, turning ephemeral structures like organ membranes and intestinal loops into a permanent three-dimensional mineral record. The physical survival of dinosaur soft tissue relies on extreme conditions: molecular shielding deep inside dense cortical bone, or rapid phosphatization in toxic, oxygen-starved water. The physiological evidence extracted from these conditions, flexible blood vessels, reproductive medullary bone, and intestinal layouts, creates an unbroken line between non-avian dinosaurs and modern birds. The fossil record serves as a molecular archive of original biology, existing alongside mineralized bone. Whole skeletons that preserve this level of internal detail will always be rare, but the handful of exceptional finds we have provide the empirical foundation for interpreting the physiology of the wider fossil record. By deconstructing the rare chemical conditions of the deep past, we have finally begun to reconstruct the living, breathing internal systems of the world's most iconic extinct animals.